This video, Gauss divergence theorem is evaluated for a vector field given in rectangular coordinate system. So we need Gauss divergence theorem. That is, surface integral of D over a closed surface is equal to volume integral of divergence of D throughout volume enclosed by the surface S. So to verify the divergence theorem for the given vector, we have to evaluate left side and right side of the divergence theorem separately and have to prove that both have same values. So let us start left hand side. Okay, so let us evaluate D over the closed surface given. So let us see what surface is given here. See, the region is defined by these values. So all the three coordinates x, y, z all vary from -1 to +1. So x, y, z all are varying from -1 to +1 means these three put together form a cube. So that is the given limits define a cube. So this is the cube. See the range of x, y, z -1 to +1. So negative value to positive value, equal distance from the center. So center, the midpoint is the origin. So the cube is symmetric about the origin. Now let us identify the locations of each face of the cube. If I take the front face, which is defined by y-axis and z-axis. The front face is defined by y-axis and z-axis. And the range is from -1 to +1. So y equal to -1, y equal to +1. Because the positive y-axis is extending towards right side. Same way, for z, the lower face is always negative and upper face is positive. Z increases upward. Similarly, the x-axis is very important one. Positive x-axis is towards us, that is coming out of the page. So that's why this point is x equal to 1. The back face point is x equal to -1. So this definition of the cube is most important here because the LHS of the Gauss divergence theorem contains integration over the closed surface. The closed surface of the cube contains 6 different surfaces. All are looking in 6 different directions. So it's very important in this kind of problems to identify the locations of each face. If you observe carefully, the front face, so let me rewrite the front face here. This is the front face of the cube. This is having a direction of a cap x, because positive x-axis is perpendicular to the front face. If this cube is having charge inside, then all the flux from the front face will be coming out in positive x direction. And this front face is exactly meeting x-axis at x equal to 1. On the complete front face, x value remains 1. So then, on the back face, same way, which is looking towards negative x-axis, x value will be -1. That means the back face of the cube meets x-axis at -1. Cut x-axis at -1 are perpendicular to x-axis and meets it at -1. Front face at 1. So x value do not change on the front face and back face. Similarly, the right face of the cube, which is going this way, is perpendicular to y-axis, positive y-axis. So direction of the right face is positive y, and this right face is located at y equal to 1. The left face is located at y equal to -1. And this is looking towards negative y-axis. Similarly, if you take up the top surface of the cube, which is perpendicular to positive z-axis and located at z equal to 1, whereas the bottom surface is looking downward or heading downward, located at z equal to -1. So identifying these directions become very important in rectangular coordinate system. So with this discussion, we shall start with the evaluation of the left-hand side, that is closed surface integration of D. So first, I split the closed surface integration into 6 different integrals. One on the front face. Similarly, second one will be on the back face. Then right, then left, then top face, then bottom. So always keep the practice of writing in this order: front face, back face, right face, left face, top face, bottom face, so that front face positive, back face negative direction, right face positive y, left face negative y, top face positive z, bottom face negative z. So let us introduce the equations to these integrals. First point is the front face. On the front face, x is always equal to 1, kept in mind. Then the d value given plus ds. Let us get back to the problem and copy the d value. D is given by the 3 components. Okay, let's copy D here. So on the front face, D value 2xyz a cap x plus 3y square z a cap y plus x a cap z dot ds ds is a differential surface element on the front face. If you consider this front face here, a differential area, that is a very small area on the front face, which is also the square form, is having the length of sides dy into dz, because front face is defined with the sides parallel to y-axis, parallel to z-axis. So any length taken parallel to y-axis is dy, parallel to z-axis is dz. So the area of the differential surface element is dy into dz on the front face. Since dy into dz, the differential surface element is a vector, its direction is a cap x. Similarly, for the back face, same dy into dz will be having direction minus a cap z. So let us get back to that equation here. Look at this one. The front face, it's easy to write in this way. The front face always looking towards x-axis. So the direction is positive a cap x. Since x-axis is perpendicular to front face, the two sides are dy into dz. So once you decide the direction, it's easy to write the differential element. If x is the direction, the differential elements must be dy into dz. Next, we shall write the equation for second integral in the same way, backwards. This vector will be same. This vector will be same. You can copy. So only thing is the equation changes here. Back face is also same as front face. Only thing is the direction is minus a cap x. Now, similarly, the right face. Same vector. Same vector. We should write differential surface element here. The right face always looks towards the positive y-axis. So apart from y, the other two, that is dx into dz, will form the side. Now the same way, the left face, the same equation. Now we can tell me what should be the ds. It's going to be same as the right phase, but with minus y-axis. Now we are left with two more integrals, one for top phase same vector. The top surface is perpendicular to z-axis. So a cap z is the direction. So the area is dx into dy. Integral over bottom surface so we copy the vector, then bottom surface is minus dx dy a cap z. Top surface positive z, bottom surface negative z. Right face positive y, left face negative y, front face positive x, back face negative x. Also, on the bottom face, z value is constant. On the bottom face, z value is constant, that is -1. On the top face, z value constant, that is +1. The top surface is always positive towards positive value, that's why it's positive number. Lowest limit is on the bottom surface. Highest limit is on the top surface, lowest limit is bottom, whether it's negative or positive, that way. So next is lowest limit is on the left side because y-axis goes towards right from left. So lowest limit, that is y equal to -1. On the right side, y equal to +1. Similarly, for the back face, so x-axis starts from the back face, move towards the front face. So this is x equal to -1. So obviously the front face is x equal to +1. So this is the crucial stage in this problem. You have to write all the values carefully. The rest is simple integration. Now if you observe carefully, and the first integral, look at this. The front face contains only a cap x component. So a cap x dot a cap x is 1, a cap y dot a cap x is 0, az dot a cap x is 0. So only corresponding components exist in dot product. So in every integral, two components will be 0. So if you perform the dot product first, then we will get 2xyz into dy dz will be present in the first integral. So now the LHS is containing few terms on the first integral, that is for x equal to 1, that is 2xyz into dy into dz. This is going to be present on the front face. Same way on the back face. Same thing will be present, but with opposite direction. That is 2xyz dy into dz. Similarly, for the left face and right face, only y component will be present in the second integral. We can easily write without saying, left face will be containing 3y square z into, so we shall go with the right face first. We shall maintain the order to avoid confusion for you later. First to right face. And right face is at y is equal to 1, perpendicular to y axis. That's why this is dx into dz. Perpendicular to y means dx into dz. Now this fellow will be integral on the left face, which is negative. Y equal to minus 1. 3y square z dx dz. The last pair we shall start with the top surface, which is at upper limit of z, that is plus 1. And what is present there is x, I guess. The z component is x. So the z component is x now. X. Top surface perpendicular to z axis. So if you leave z, you will be having dx into dy. Here it is minus bottom surface z equal to minus 1 x dx into dy. Next is the integration. Let us see what happens to the first integral here. Integration is to be performed with y and z. So one y is there, one z is there, two variables. X is constant. X is to be substituted with 1. So 2x goes outside. Y and z will be integrated. So 2x will be outside. For the x, I'm going to substitute 1. One integration is for y. That is going to be y into dy. Y is present. Another one is z into dz. Limits minus 1 to plus 1 for all variables. Similarly here, 2 constant outside. X is also constant outside, but x value is going to be minus 1. For the back face, integrate y dy, integrate z dz with the limits minus 1 to plus 1. Similarly, we write other two. Integration on the right face, this is with respect to y and x and z. So y is constant, so 3 outside. Y square is also outside, but y value is 1, so 1 square. Y square becomes 1 square. First integral contains only dx. Second integral contains z into dz. Limits are minus 1 to plus 1. Here same way, 3, but y value is minus 1 whole square. Dx minus 1 to plus 1, z dz minus 1 to plus 1. The last pair, that is integration with x and y, no constants. So x dx, then y minus x dx integral of -1 to dy. So there are no constants, no z on the last pair. We can easily observe that the last pair gives us 0. Integration of x from -1 to 1. Here also integration of x from -1 to 1. Dy integration. So no need to carry out this integration. This gives us 0. Now we shall find the value of other two. So the LHS is equal to 2 into 1 is 2. Integration of y is y square by 2. The limits -1 to +1. Integration of z is z square by 2. -1 to +1. Here is -1 to minus plus 2 here. Again y square by 2. And z square by 2. These two terms are not cancelled because of their positive term in between. Similarly, other term. 1 square is 1, so 3 into 1 is 3. Integration of x dx is x. -1 to +1. Z is z square by 2. Next, -1 square is positive, that is 3 here. X is -1 to +1. Z square by 2 is -1 to +1. So by inspection, you can easily check the answer of the second pair. That's going to be 0. See, left side, first part and second part in the last pair is same with opposite polarity. So that's why no need to carry out this integration, they get cancelled out. So now here 2, apply the limits. 1 square by 2 minus -1 square by 2. Z also same thing, 1 square by 2 minus of -1 square by 2. Plus 2 into again 1 square by 2 minus 1 square by 2. Right? So now we can easily see here 1 square by 2 is 1 by 2. -1 square is also 1 by 2. This is going to be 0 and this is going to be 0. So total answer on the left side is 0. So there is vector D, but the total electric flux leaving the closed surface is 0. Now we have to evaluate the right hand side of the Gauss divergence theorem. That's going to be triple integral of del dot d into dv. So before that, we shall find divergence of d separately. That is partial derivative of dx, dy and dz. Now we have to find out what is dx, dy and dz. So we should move to the problem where D is present. Okay, keep the vector D here for reference. Now check here. What is dx? Dx is the x component, that is 2xyz. Dy is the y component, that is 3y square z. And dz is the z component. So the divergence of D is equal to dou by dou x of x component 2xyz plus y component of 3y square z plus z component of x. So after differentiation with respect to x, you are left with 2yz. 2yz are constant because differentiation is with respect to x. Differentiation of x is 1. Similarly, here 3 is constant, z is constant. You have to differentiate y square. Y square differentiation is 2y. Z remains same. The last one is the differentiation with respect to z. So there is no z at all. That's why it's going to be 0. So we have 2yz plus 6yz. 2yz, 6yz, total 8yz. 6 plus 2. Why is that common factor if you take 6 plus 2? 8. 8yz. Now, the right-hand side is the triple integral of del dot D, nothing but 8yz. Differential volume in dV. dV is dx into dy into dz for Cartesian coordinate system. Now triple integral with respect to x, y, z, 8 is constant. First integral is with respect to x. There is only dx. Second with respect to y. So this is y dy. Third one with respect to z. That is z dz. Limits are -1 to +1, -1 to +1, -1 to +1. Triple integration 8. This is x -1 to +1. Y is y square by 2 -1 to +1. Z square by 2 -1 to +1. 8. This is going to be 2 because upper limit 1 minus of -1 is 2. And in this case, we'll get 0 because it's going to be 1 square by 2 minus 1 square by 2 will make it 0. Z also 1 square by 2 minus 1 square by 2. This gives us 0. So left hand side and right hand side are equal. So the right hand side, which is having a value of 0, which is also equal to the left hand side. Hence the theorem. So we have proved the Gauss divergence theorem.